Hello, I'm Ralph Gable of the Electronics for the Inquisitive Experimenter YouTube channel. So you have that transmitter and you want to know how much power it's putting out. So you go out and you buy an SWR wattmeter to find out what the truth is. The problem is that this SWR wattmeter isn't actually 100% accurate. Every measurement instrument is only accurate within certain tolerances. Now, some are better than others. What I'm going to present here today is an alternate method of measuring the power output of your transmitter. Now, frankly, my motivation is that I don't want to spend yet another $183 on yet another element for my Bird 43 for the occasional test that I just might choose to do. Yet, I need to have some confidence that the power that I'm measuring is reasonably accurate. Now, as a matter of note, I will place a link to a PDF which contains a lookup table for dBm-to-Watts and Watts-to-dBm. Furthermore, I will also place a link to the original Excel file that I created to generate this lookup table. At the end of this video, I will quickly present a way of making this measurement with a bucket of water. Yes, with a bucket of water. If you have questions or comments, please feel free to add a comment to this video. If you find this video helpful, please click on the like and don't forget to subscribe. So let's begin with a better explanation of my own motivation to find a better way. I own a Bird 43 wattmeter. Now, these things aren't cheap, but this model has been around for decades and is still being sold new from the manufacturer. They have been the go-to instrument for reliably measuring power industry-wide. You change the frequency and power range by changing the element which is inserted into the pocket into the front of the meter. The Bird 43 has a stated accuracy of plus or minus 5% of full scale. My plan is to use my Bird wattmeter to evaluate the output power of this Baofeng GT5TP that I borrowed from a fellow ham. Now, they claim an output power of 8 watts. Now, Bird has a 10-watt element that would suit this kind of testing very nicely. This would give me a tolerance of plus or minus 0.5 watts, which would be quite sufficient. The problem is that I just don't want to drop another $183 on yet another element just because I don't do this kind of testing enough to warrant this kind of cost. The lowest power element that I own for this frequency range is 50 watts full scale. So at plus or minus 5%, this means the tolerance is going to be plus or minus 2.5 watts of reality. That means that with this 50 watt element, the Bird could report anything from 5.5 watts to 10.5 watts and still be within its stated tolerance if the HT is outputting a genuine 8 watts. But what if it's not? How would I even know that with this wide tolerance? I needed something more accurate. Now, let's talk about the solution that I came up with. This procedure is using my Bird 43 in-line wattmeter with a sampling element that I already own. The beauty of this sampling element is that you can monitor the output of a transmitter with a spectrum analyzer looking for spurs or modulation characteristics, a number of different things. Now, as a side note, DX Engineering sells what appears to be a Bird 43 clone manufactured by Coaxial Dynamics. The procedure is the same whether you're using the Bird 43 or its clone. The core of this procedure is to measure the signal level of the output of this sampling element and then back calculate to the original power level being passed through the wattmeter. The output of the Bird sampling element for 25 megahertz to 1000 megahertz is 50 dB plus or minus 2 dB. Now, what exactly does that mean? Well, let me give you an example. Suppose I'm passing 100 watts through the Bird wattmeter. Now this translates to plus 50 dBm. The output of the sampling element will be 50 dB below this value. So let's do the math. We have power running through the bird plus 50 dBm. We have attenuation of the sampling element, 50 dB. So the nominal output power on the output of the sampling element will be 50 dBm, the power running through, minus the 50 dB of attenuation, or 0 dBm. But the attenuation has a tolerance of plus or minus 2 dB. So the actual output could be anything from minus 2 dBm to plus 2 dBm. In its simplest form, this procedure consists of measuring the signal level from the output of the sampling element using a spectrum analyzer, adding 50 dB to this measurement, and then looking up the resulting number in a table or breaking out the calculator and calculating the number. If our goal is to improve the accuracy of our measurement using this method, then we have a little bit of a problem with this simplest form. So let's consider a 5 watt HT output, which when converted to dBm is 36.99 dBm. To get the output of the sampling element, we subtract 50 dB from this to give us a nominal of minus 13.01 dBm. But this 50 dB has a tolerance of plus or minus 2 dB. We add this into the measurement uncertainty of the spectrum analyzer, worst case, plus or minus 0.4 dB. So the total uncertainty is now plus or minus 2.4 dB. So this output could be measured at anything from minus 15.4 dBm to minus 10.6 dBm. If all we do is add 50 dB to this to get the original power level, we would get an original power level anywhere from 34.6 dBm to 39.4 dBm, which translates to 2.884 watts to 8.71 watts. Well, with the native accuracy of the bird giving a potential reading from 2.5 to 7.5 watts, we really haven't done anything to improve our accuracy. Furthermore, we have not taken into account the loss of the cable from the transmitter to the wattmeter or from the sampling element to the spectrum analyzer. But what if we knew what the actual losses were for the entire signal path from the transmitter through the bird to the spectrum analyzer? Now, if we knew this, we could eliminate this aspect of the inaccuracy to the degree that we can measure it. We would be left with just the measurement uncertainty of the spectrum analyzer itself, which they claim at less than 0.4 dB. There are 3 ways we can determine this. 2 of these use our spectrum analyzer, and 1 uses the nanoVNA. Way 1 uses a signal generator and a spectrum analyzer. Way 2 uses a spectrum analyzer with its own tracking generator. And way 3 uses a nanoVNA or similar device. All 3 requires us to make this measurement using all the cables and adapters that we will use in the final power measurement. So the object is to completely characterize the entire system. The only difference between way 1 and way 2 is the source of the test signal. The process for them is exactly identical in every way other than that. So let's start with these 2. Okay, so let's get started.
Step 1.
The first step is to set up our test instruments for the measurements to be made. We set the signal generator or spectrum analyzer's tracking generator such that the input to the spectrum analyzer is going to be happy. In my case, I'm going to use minus 10 dBm amplitude. Now, because I'm checking the output power of an HT that's currently set up to talk to a local repeater, I will set the signal generator's output to 147.84 megahertz, the transmit frequency of the HT. I'm going to set up the spectrum analyzer for a span of 100 kilohertz and a center frequency of 147.84 megahertz. In order to give an accurate power reading of the transmitter's output power, the resolution bandwidth, or RBW, needs to be set wide enough so that the entire signal bandwidth resides within the window. Now, I'm going to set both the RBW and the VBW, or video bandwidth, to 30 kilohertz. Next, I will consider the type of trace I will use. Now, normally you might have to do some visual averaging as you watch the numbers jump around on the screen. In my case, I'm going to use a power average trace so I can get a nice stable number to grab with a whole lot less work. I will set this to do 50 averages.
Step 2.
Now we connect the signal generator or tracking generator's output directly to the spectrum analyzer's input and enable the RF output.
Step 3.
Either do the fancy eyeball averaging or reset the average on the spectrum analyzer trace. Once the average is complete, I set the spectrum analyzer's marker to sit right on 147.84 megahertz, my test frequency. Note the signal level. Here you can see that I measured minus 9.99 dBm.
Step 4.
Now we disconnect the signal generator or tracking generator output from the spectrum analyzer's input. We connect it to the point where the transmitter is going to be connected. We connect the cable from the output of the sampling element to the input of the spectrum analyzer.
Step 5.
Either do the fancy eyeball averaging or restart the average on the spectrum analyzer trace. Once the average is complete, note the new signal level. Here you can see that I measured minus 59.30 dBm.
Step 6.
Now we get to do the math. We subtract the second number, don't forget the sign, from the first number. So the first number was minus 9.99 dBm. The second number was minus 59.3 dBm. So the result is minus 9.99 minus a negative 59.3, which is the same thing as minus 9.99 plus 59.3, which equals 49.31 dB of attenuation. Now we know the attenuation through the entire system from what will be the transmitter's output to the input of the spectrum analyzer. But you know, there's an easier way to accomplish this, which some might say is more accurate. We will use our nanoVNA. So we fire up our nanoVNA, and I'm going to connect it to the computer and use the VNA Saver program. Being that this is not a video on how to use a VNA, I'm going to assume that you already have some knowledge there. So this is how I'm going to set things up in the nanoVNA Saver program. I'm going to have a span of 100 kilohertz, a center frequency of 147.84 megahertz. In sweep settings, I'm going to choose an average sweep. I set the number of measurements for the average to 10. Now, you can make this whatever makes you comfortable. We have to calibrate it for a through, gain, or S21 measurement. We want to do this in such a way that we include as many of the adapters that we need to make the ultimate measurement as possible. I have completed the calibration at the end of the cables where I will be connecting to the bird assembly. Now we connect port 1 to where the transmitter would normally be connected, and port 2 to where the spectrum analyzer would be connected. We do our sweep and read the S21 gain number from our marker data. What I see here is minus 49.437 dB. This is the attenuation of the bird assembly from where the transmitter will connect to where it is connected to the spectrum analyzer. Notice how similar the numbers are between the two methods. Now we get to measure the actual output power of our representative HTs. Our first step in measuring the output power of the HTs is to get everything connected up. I connected the first HT, which is the aforementioned Baofeng GT5TP, to the input side of the bird wattmeter. I connected the output of the sampling element to the input of the spectrum analyzer. Now I key up the HT, reset the power average on the spectrum analyzer, and watch as the average number climbs to 50. When it reaches 50, I freeze the trace and read the power level from the marker data. The marker data reads minus 11.95 dBm. The attenuation of the whole measurement rig, remember we measured it at minus 49.437 dB. Now we get to do a little math. Marker data plus attenuation equals the actual power output of the HT in dBm. So we have minus 11.95 dBm, which is what we measured on the spectrum analyzer, plus the 49.437 dB, which is the attenuation of the system, is equal to 37.487 dBm. Now we can look this up, and the closest value to this on the dBm-to-Watts table, or we can do a little bit of math. The formula is equal to the power is equal to 10 brought to the power, your dBm reading divided by 10 minus 3. So in this case, power is equal to 10 brought to the 37.487 divided by 10 minus 3 gives us 5.607 watts. Not exactly 8 watts, is it? Now, let's see what these other two are doing. I will start with the Yaesu FT70D. I get a reading of minus 12.97 dB on the spectrum analyzer, which gives us 36.467 dBm output power, and that translates to an output power of 4.433 watts. And this is rated at a 5 watt output, so that's not too bad. Then this very, very old and tired ICOM IC2GXAT, whose battery is not terrifically stellar. Remember, low battery voltage means low power output. So I get minus 16.11 dBm measured on the spectrum analyzer, and that translates to 33.327 dBm power output, which translates to a power output of 2.15 watts. Now, for the promised alternate method of power measurement. Yes, this alternate method begins with a bucket of water, but not just any water. It must be 100% pure distilled water. You have to know how much mass it has in kilograms. Next, we have to have some sort of purely resistive 50 ohm load which can act as our dummy load and the heat producer. You will need a means of accurately measuring the temperature in degrees Celsius and the time in seconds. We connect our transmitter to the dummy load and then immerse it into the water. We carefully measure the initial temperature of the water in degrees Celsius. Now we key up that transmitter and transmit into the dummy load for a specific amount of time while monitoring the temperature rise of the water. Once the water temperature has risen sufficiently, or we have reached our predetermined measurement time, we unkey the transmitter and wait a little while for the water temperature to become homogeneous. Maybe carefully stir it a little bit with a wooden something. Now, you don't want to suck any heat out of the water, so don't use a metal anything to stir. Now we measure the final temperature of the water in degrees Celsius. The specific heat of water is 4,137.9 joules per kilogram degree Kelvin. A change of 10 degrees Celsius is also a change of 10 degrees Kelvin, so don't sweat that. Using the specific heat and mass of the water and the temperature rise in degrees Celsius, we can calculate the number of joules of energy that have been added to the water by the transmitter to cause the rise in temperature. So we have 4,137.9 times the mass of the water in kilograms times the change in temperature in degrees Celsius is equal to the energy put into that water in joules. Now, knowing this number of joules of energy and the time it took to add that energy, you can calculate the number of watts of the transmitter. So watts is equal to the joules that we just calculated divided by the elapsed time in seconds. Now, I've never actually done this myself. It is a laboratory way to accurately measure power applied, which they told us about in our U.S. Air Force metrology training. It might be fun to try it sometime, I don't know, just for giggles. If you're mindful of your finances as I am, and you already own a sampling element for your bird wattmeter, then this is a great way to avoid having to drop big bucks for a one-time power measurement. If you don't have a sampling element, I recommend that you buy one of these. It's ever so handy on so many levels, with this being just one of them. If you found this video helpful, please click on the like and don't forget to subscribe to the channel. Thank you so much for watching. Until next time, toodle-oots.